Welcome everybody to my first video for Math 2305, Discrete Mathematics. In my videos, I'm going to be covering this section by section, here starting with section 1.1. And for each chapter and section that's covered, I have a handout to go along with the videos, which lists out the definitions, proofs, and examples that I'm referring to. So if I don't have something on my video on screen, you may refer to the handouts to have the additional information for what I'm referring to. So here we're starting with section 1.1. And to begin, I kind of want to clarify something specific about discrete versus continuous. So we're going into these subjects that are encompassed into the topic of discrete mathematics. So what does that word actually mean for us here? Well, discrete is standing for something which is constituting a separate entity or is individually distinct. Discrete means it can take only particular distinct values and not other values in between. This is in contrast to continuous, which means uninterrupted in space, time, or sequence. And so continuous means it can take on any value within a given interval. So a specific example of discrete would be our integers. Integers, by that I mean numbers like -2, -1, 0, 1, 2, and so forth. These are individually distinct numbers without any in-betweens. For instance, there's no numbers between 1 and 2 within the integers. It's just 1 and 2 individually. And so that is what something which is discrete looks like. In contrast, an example of something continuous in terms of numbers would be the real numbers. So the real numbers, we often visualize those on a real number line, from negative infinity to positive infinity. And so it's not broken up, it's a continuous line representing all real numbers. For instance, you can always find a number between two values on the number line. Between 0 and 1, you could find 0.5, and you could go even further to like 0.2. And so there's always an in-between. It's not broken apart like it is in the situation of integers. So that's what we're going to be dealing with primarily in discrete mathematics. Things that can be listed out into discrete components, much like we can list out in each individual number in the integers. So looking in section 1.1, and the first example we're going to be dealing with is just looking at how do we count or figure out the number of integers or numbers there are between two given values. So here it says, how many numbers are there between 1 and 10, between 1 and 1,000, or between 1,000 and 1 million? So especially within some of the things we're going to be doing here, we need to be very clear about what we mean in our statement or question. Two specific things that come to mind are, what is it referred to by numbers? We need to be very specific about what kind of numbers we're going to be dealing with. Are we dealing with the aforementioned integers or something else? Like, is this supposed to refer to real numbers? Or maybe the rational or irrational numbers? There's a lot of different choices we can have here. And again, integers I wrote out a second ago, and rational numbers are numbers like 1/2 or 2/3. Numbers like that are being referred to as rational numbers. Any number that can be wrote as the division of two integers is a rational number. That even includes integers as well. And irrational numbers, things like √2 or the √3, numbers that cannot be represented as a rational number are considered irrational. So for this particular problem, it's really only going to make much sense if we use integers to be the numbers that we're counting between two given values. For instance, if we start off with the numbers between 1 and 10, it's not going to make much sense to list out real numbers or rational numbers. That would take way too long and indeed would be mostly impossible to consider within the problem that we're trying to answer here. So if we just list out all the positive integers, we go 1, 2, 3, 4, 5, and just do a simple count up to 10. Now the next thing we might consider is when we say between, do we mean including or not including the two numbers at the very end on the left and the right endpoints? So in this case, we're going to refer to between as inclusive of 1 and 10 or 1 and 1,000 and so forth. So we're going to count those numbers in as well. So we can see pretty clearly that when we deal with just positive integers and inclusive of between, we have 10 positive integers between 1 and 10. A fairly simple count of the numbers, not a whole lot more to say. This also applies to between 1 and 1,000. There would be 1,000. We could write them out if we want to, but it's pretty clear to see if we go from 1 and then go 1, 2, 3 up to 999 and 1,000, we're going to have 1,000 positive integers there. Now the interesting thing comes when we start looking at things like between 1,000 and 1,000,000. Now it's not quite so clear exactly the count, even though we can tackle this in a variety of different ways. Let me list out one way of approaching this idea. We can start out by listing out 1, 2, 3, and then go all the way up to 999. And then from there go 1,000, and then 1,001, and then that goes all the way up to 999,999, and then 1,000,000. And so with the same reasoning that we were looking at up above, the positive integers between 1 and 999 would be 999. And the number of positive integers from 1 all the way up to 1,000,000 would be a total of 1,000,000. And so we can consider then the way of counting up the number of positive integers from 1,000 to 1,000,000 inclusive would be to take the 1,000,000, subtract out the first 999, and what we'll be left with is 999,001. And that would tell us then the number of positive integers between 1,000 and 1,000,000. So this is sort of a practical approach of figuring out a count of the number of things, or in this case, positive integers between two values. Now, what we're going to be dealing with a lot, though, in this class specifically, are sort of a generalized statement that we can either prove or disprove for any numbers, in this case, positive integers. We'd like to also know what a formula would look like for finding the number of positive integers between two values. Well, let's approach it this way. So we're going to generalize. Generalize means to use, in this case, variables in order to make it work for any potential values we might run into. So let's look at it this way. Let's let the number or the letter M stand in for the smaller of the numbers, 1,000, and let the letter N stand in for the larger of the two, the 1,000,000. And then we can look at the 999 in this case being 1 taken away from the 1,000, or m minus 1. So what we just did here down below is to take the n, which is the 1,000,000, and subtract away the 999, which is n minus 1. And so the basic formula then would look like n minus m minus 1, or that would be the same thing as n minus m plus 1. And now this is the formula, but we have to understand we created this formula under very specific conditions where the n and the m are standing for only positive integers. So let's take this generalization of it and write a general statement of what we're dealing with here when we talk about this situation and specifically this formula. So I'm going to start off this by saying if. A lot of our statements this semester will start off this way. If m and n are positive integers, so those are the two numbers we start out with, the 1,000 and the 1,000,000. With another specific thing we have to say, m is less than or equal to n. One has to be smaller than or equal to the other. That's our assumptions, our hypothesis we'll call it. Then, as a result, the number of positive integers, and we're going to use a letter to stand for the number of positive, or all the positive integers which stand between those two. We'll call that I, the number of positive integers I, with m less than or equal to I, less than or equal to n, and that is then all the numbers which sit between the two numbers m and n, is given by n minus m minus 1, or n minus m plus 1. And so this is a very rigorous statement which takes into account all the different parts of the problem, of the statement, and sets up each individual variable specifically for what it needs to be. It sets up the m and the n as positive integers with one less than or equal to the other, and then sets up the number of positive integers between the two, counting those up with the letter I, is given by this formula here. So the general structure of this is we have a if statement, and that if statement takes the hypothesis or the assumptions of the statement. And so we start out with those like we did before. Hypothesis and the assumptions, and then from there it's supposed to follow the conclusion. So in our case, the hypothesis / assumptions were that we had m and n as positive integers with m less than or equal to n, and the conclusion was the number of positive integers is given by our formula n minus n plus 1. So we're going to set up a lot of statements in this fashion. If something, then something. Now with that in mind, let's look at how to count the number of positive integers between -10 and 90. Still not a terribly involved type of problem, but does it fit within the same reasoning that we had up above? It does turn out to be that way. However, when looking at the statement that we had up above, we don't actually have anything about negative integers, but just positive integers. So all of our assumptions were based upon that to begin with. And so if we had the letters M and N to stand in for -10 and 90 respectively, that wouldn't fit within the problem statement up above, so we could actually automatically assume that the same would hold true in this situation, the same conclusion that is in the same formula. So why don't we go ahead and transform it into the situation we had up above. So consider that we had -10 less than or equal to, and then I is going to stand for all the numbers between that one and 90. So we'll set this up as -10 less than or equal to I less than or equal to 90. And then if I add 11 to everything here, it would change it into 1 less than or equal to I plus 11 less than or equal to 101. And so the situation now turns out that the smaller number n would be 1 and the larger number n would be 100, and I would still count all the numbers between 1 all the way up to 101. So in this case, the situation still turns out to be pretty much the same as we had up above. There are, again, n minus m plus 1, which would be equal to 101 minus 1 plus 1, or just 101 integers between -10 and 90. And so it applies the same way. However, we should cross out the word positive integers here because we're not dealing strictly with positive integers anymore. So that brings us to our first, what we're just going to call fact for now. And so that'll say if m and n are any integers with m less than or equal to n, then the number of integers I such that m is less than or equal to I less than or equal to n is n minus m minus 1, or n minus m plus 1. Now this statement seems reasonable from our rationale and what we've seen so far, but it's still strictly unproven. So as we go along, we're going to talk about more when we need to really start getting serious about really proving things as true across all possible values of our unknowns, in this case our integers. So for now, we're going to leave it unproven strictly, but reasonable from what we have seen so far as applying to all integers.